Hello everyone and welcome you all in the problem solving class of the course Applied Electromagnetics for Engineers. I am Vivek Kumar Srivastav, PMRF Research Scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper. So in this session, we will see some of the numerical based on the topics such as boundary condition, Poisson's equation and Laplace equation. So let us start the today's class. So here is the first problem. The problem states that the Poisson's equation of a homogeneous region where epsilon is independent of a partial variable is defined as option A del square V is equals to 0, option B del dot epsilon del V is equals to minus rho V, option C del square V is equals to minus rho V by epsilon, and option D is none of the above. So for uh, obtaining the Poisson's equation, first of all we have to know that what this homogeneous region states. So homogeneous region is a region where epsilon, that is the relative permittivity, is independent of the spatial variable. That means epsilon should be constant throughout the region. Okay, epsilon should be constant throughout the region. Okay, so now once you know that what is basically a homogeneous region, so now let us move ahead and derive the Poisson's equation. So for deriving the Poisson's equation, we have to first takes the first Maxwell's equation, which is in the point form is defined as del dot D is equals to rho V. Okay, so as we all know that D, that is electric displacement vector, is defined as epsilon times E. Okay, so now let us replace the value of D in this equation. So this becomes del dot epsilon E is equals to rho V. And we also know one constitutive relationship, that is E is equals to minus del V. Basically this equation gives you the relationship between electric field and the electric potential vector. Oh, sorry, electric potential, not, it's not a vector. So now let us replace the value of E here and place this E is equals to minus del V. So this becomes del dot epsilon minus del V is equals to rho V. Okay, so here, as we know that this we are deriving for homogeneous region where epsilon will be constant, means it does not depend on the spatial variables. Okay, so basically we can take epsilon constant here. So this becomes minus epsilon del dot del V is equals to rho V. So this can be further simplified as we all know that del dot del is defined as del square, so we can easily replace del dot del as del square. Okay, V is equals to minus rho V by epsilon. So this basically the Poisson's equation. Okay, this is how we can derive the Poisson's equation. And also a special case of this Poisson's equation is where rho v is equals to 0. So basically this defines the Laplace equation. Okay, so Laplace equation is defined as del square v is equals to 0. So this is a Laplace equation, whereas this equation is the Poisson's equation. Okay, so option C is correct here. Okay, so the second question is, the uniqueness theorem states that option A, if V satisfies the Poisson's equation or Laplace equation and the prescribed boundary condition, then V is the only possible solution for the given problem. Option B states that if V satisfies Poisson's or Laplace equation and the prescribed boundary condition, then more than one possible solution for the given problem. Okay, option C states that if V satisfied Poisson's equation and or Laplace equation and the prescribed boundary condition, then there is no solution for a given problem, and option D is none of these. So the correct answer of this question, that is the uniqueness theorem, is option A. So basically uniqueness theorem states that if suppose V is satisfy both the Poisson's equation and the Laplace equation, okay, if V satisfy both the Poisson's or Laplace equation and for a within prescribed boundary condition, then V is the only possible solution for it for the given problem. So option A is correct here. So now the third question is, in the free space V is defined as 6xy square z plus 8. So here V basically potential field. Okay, so the electric field we have to find out at the point mentioned at 1 comma 2 comma minus 5. So as potential is given and we have to find electric field, so we can use the constitutive relationship, that is E is equals to minus del V. Okay, so this can be represented as del by del x cap plus del by del y cap plus del by del z cap into the potential that is given to you, that is 6xy square z plus 8. Okay, so now you can differentiate this function with respect to its partial variable, and this becomes 6y square z x cap plus 12xyz y cap plus 6xy square z cap. Okay, so this basically represents the electric field vector. Now for finding out the electric field at the point mentioned as uh, point P, which is given to you 1 comma 2 comma minus 5, you have to just put up the value of x, y and z as 1, 2 and minus 5 in this equation. Okay, so electric field, once you put the value here, you can find out. So electric field, the value of electric field at this point, at the point given in the question, is defined as 120 x cap plus 120 y cap minus 12 z cap volt per meter. Okay, so now moving ahead, in the previous question we have to determine the volume charge density in picocoulomb per meter cube at the same point which is specified in the previous problem as well. Okay, so we have to determine the volume charge density. So now for solving this problem we will use the Poisson's equation, okay, which is defined as del square V is equals to minus rho V by epsilon. Okay, so del square V is written as del square by del x square plus del square by del y square plus del square by del z square into the potential which is given to you in the previous problem, which is equals to 6 x y square z plus 8. Okay, yeah, so it is given to you in the previous problem. Okay, which is equals to minus rho v by epsilon. So now we will double differentiate this function with respect to x, y and z, okay, for evaluating the value of rho v. So once we differentiate this function with respect to x, so this becomes 0. Okay, now we will differentiate this function with respect to y, so this becomes 12xz, and again when we differentiate this function with respect to z, then also this function will becomes equals to 0. This derivative becomes equals to 0, and this will be equals to rho v by epsilon. Oh, I am sorry, rho v by epsilon. So this rho v becomes equals to minus 12xz into epsilon. Okay, so point x and z is already given in the question, which is equals to 1 and minus 5. So you can directly put the value of x and z, and the epsilon value you can take as a air media, because it is not specified in the question here. So here also it is given that we are solving for free space, so you can take the epsilon for free space, which is equals to epsilon naught. Okay, so you can put the value and find out the value of volume charge density. Okay, so that's how you can solve such type of questions. So now moving ahead, the next question states that two homogeneous dielectric region 1, which where rho is less than equals to 4 centimeter, and region 2 where rho is greater than equals to 4 centimeter, have the dielectric constant 3.5 and 1.5 respectively. If d2, that is displacement vector in the region 2, is given as this, okay, then we have to find out the electric field E1 means in the region 1. Okay, so first of all see that how to visualize such type of question in pictorial form. So here we are considering the cylindrical coordinate system. Okay, so let us suppose this is my cylinder, and so basically this is the radial vector, okay, rho. Okay, so when we are talking rho less than equals to 4 centimeter, so this represents region 1, whereas for rho greater than 4 centimeter, this represents the region 2. Okay, so here epsilon means the dielectric constant is given as 3.5, whereas dielectric constant for region 2 is given in the question, which is equal to 1.5. Okay, now d2 in region 2 is defined as 12 a rho minus 6 a5 plus 9 az. Okay, so we have to find out that what will be the electric field inside this cylinder. Okay, so for solving such kind of problem, we have to first see the boundary condition. Okay, by using boundary condition we can easily solve such type of question. So as we all know that at the boundary, if suppose this is the boundary, okay, so here the tangential component of electric field will remains the same, that is e t1 and e t2, if suppose this is region 1 and this is region 2, whereas the normal component of d will be continuous, so d1n and d2n. So from here we can say that et1 will be equals to et2, and d2n is equals to d1n. Okay, so basically this condition only satisfy when there will be no surface charge present at the boundary. Okay, so here also in the question it is not specified that, that's why I am directly taking that at the surface there will be no surface charge present, so that's why I am directly writing that d2n minus d1n. Okay, if suppose surface charge will be present, so the equation will be n dot d2 minus d1 equals to rho s. Okay, then you have to apply this uh, this equation instead of this. Okay, but here in this question, as it is not mentioned in the question that any surface charge is present, so we can directly use this expression. Yeah, so once you understand that at the boundary the tangential component of electric field and normal component of displacement vector will continuous, so we can use this two expression for finding out the electric field inside this cylindrical volume. Okay, so first of all, d2 is given to you, which is equals to 12 a rho minus 6 a phi plus 9 az. Okay, so for finding out the normal component of density, normal component of displacement vector d2n, what you will do, you will just take a dot product with respect to the normal component. Okay, which is equals to a rho here. Okay, so take a dot product, so d2n will be equals to n dot d2, and here n is a rho dot 12 a rho minus 6 a phi plus 9 az. Okay, so normal component of displacement vector in region 2 is defined as 12 a rho. Okay, so now the tangential component in region 2 is obtained as d2. Here this is a vector quantity. Okay, so you can directly subtract the normal component from the d2, means displacement vector present in region 2, so you can directly subtract and find out the value of tangential component, which is equals to minus 6 a phi plus 9 az. Okay, so that's how you can find out the value of normal and tangential component of yeah, normal and tangential component of displacement vector in region 2. So now once you find out the value of normal component of, yeah, tangents tangential and normal component of uh, displacement vector in region 2, what we have to do, in region 1 we can find out the normal component will remains the same. Okay, so d1n will be equals to d2n, which is equals to 12 a rho. Okay, whereas for finding out the tangential component of d inside this region, what we will do, we will take the second expression, that is t e2t is equals to, or sorry, e1t is equals to e2t. Okay, so what we have to do, we have to uh, convert this in the form of displacement. So we have to just divide the electric field with the uh, we have to just divide the displacement component of tangential field with their respective dielectric constants. d1t by epsilon 1 is equals to d2t by epsilon 2. Okay, so d1t is obtained as epsilon 1 by epsilon 2 into d2t. Okay, so epsilon 1 is given here, uh, 3.5 epsilon naught over 1.5 epsilon naught into yeah, tangential component of density in region 2 is obtained as 6 minus 6 a phi plus 9 az. Okay, so you can calculate the value of tangential component, and normal component we have already find out. So the total dense displacement vector inside this cylindrical object is obtained as d1n plus d1t. So that's how you can find out the value of d. Once you find out the value of d, you can obtain the value of e as e1 as d1 over epsilon 1. Okay, so that's how you can calculate. So now moving ahead. So in the previous problem, determine the polarization loss vector in region 2. So first of all, we have to understand that what is basically a polarization loss. Okay, so if suppose this is a dielectric media, so once you applied the electric field in this dielectric media, okay, so the atom which is inside this dielectric media get polarized, okay, which is defined like here. So this is basically a small dipole. That's how I am representing. Okay, so this polarization is defined as displacement vector d is equals to epsilon naught e plus p. Okay, so basically p represent here the polarization loss factor, and this can be represented as epsilon naught xi into e. Okay, so we can take epsilon naught constant here and e as constant, so this becomes 1 plus xi, and we can also represent this as epsilon naught times e. So inside the dielectric media you can use this expression. Okay, I think you already know this expression can be used for a dielectric media where epsilon r represent the relative permittivity of the dielectric media. Okay, so we will use this expression for finding out the polarization loss vector, and which is equals to epsilon naught xi 2, because we are finding out the this inside the region 2. Okay, and we will take e2. Okay, so how to find out the value of zeta 2? Okay, so zeta 2 we have already derived. This becomes equals to 1 plus zeta 2 is equals to epsilon r. So basically epsilon r is given here in the question, which is equals to 1.5. So we will take this for finding out the value of xi2 is equals to 1.5 minus 1, and it is equals to 0.5. So we have to just replace the value of zeta 2 here, and this becomes equals to epsilon naught into 0.5 into e2. Here e2 is given in the question. Okay, so this becomes 12 a rho minus 6 a5 plus 9 az. Okay, and we have to divide this by epsilon naught into epsilon 2. Okay, let us say it's epsilon 2r, relative permittivity of media 2. Okay, so yeah, so basically epsilon naught will cancel each other, and this will be equals to 1.5. Okay, so this basically equals to 3. So the polarization loss vector in region 2 is obtained as 4 a rho minus 2 a5 plus 3 az. So this is how you can find out the polarization loss vector. So let us move ahead. Yeah, the unit becomes nanocoulomb per meter square. So let us move to the next problem. So we have to find out the energy density in region 1 for the previous problem, that is problem 5. Okay, so here in for this problem we have to find out that how much will be the electric sorry, yeah, energy density. So energy density basically uh, one, give me a moment. Yeah, so energy density is defined as half e dot d. Okay, So inside the electrostatic field, how much energy is stored, that's defined the energy density. Okay, so we have to find out the value of energy density inside the region 1. So inside the region 1 we have already find out that what will be the value of uh, d and e. Okay, we have all find out the value of d. Okay, so we will use this uh, and find out the value of energy density. So we can put the value as 1 by 2. D will be this will be equals to d by epsilon naught into 3.5 into d. Sorry, this will be dot product. Okay, so that's how you can calculate the value of energy density inside region G, in inside region 1. Okay, so the value of energy density after calculating this becomes equals to 12.62 millijoule per meter cube. Okay, so I hope that you find out the step that how to solve such kind of problem. Okay, so this will be clear to you after this problem. So let us move to the next problem. So here the question states that given the potential field which is equals to 2x square yz minus y cube z exist in a dielectric media having epsilon is equals to 2 epsilon naught, does not satisfy the Laplace equation. So here in the question it states that uh, the potential field does not satisfy the Laplace equation. So there is a possibility that this will satisfy the Poisson's equation, that is given as del square v is equals to minus rho v by epsilon. Okay, so we have to find out the total charge within the unit cube. Okay, so if suppose this is a cube and inside this cube some charge will be present which is defined as rho v. Okay, so we have to find out the total value of charge, that how much charge is present inside this cube. Okay, so for finding out this rho v we will use Poisson's equation. So first of all we will uh, derive the value of del square v, which is equals to del square by del x square plus del square by del y square plus del square by del z square, 2x square yz minus y cube into z. Okay, so we can calculate the value of del square here, which is equals to 2yz, and this becomes 0 minus 6yz, and this will be equals to 0. So overall del square we obtained as minus 4yz, and this will be equals to minus rho v by epsilon. So rho v we can find out as rho v is equals to 4yz into epsilon. So epsilon is given in the question which is equals to 2 epsilon naught. So you can directly put the value of epsilon here. Okay, so once you obtain the value of rho v as yeah, this will be equals to 8 yz into epsilon naught. So this is for the small infinitesimal volume. Okay, so for finding out the total volume charge inside this cube you have to integrate it. Okay, you have to integrate and take the limit which is mentioned in the question from 0 to 1. Okay, yeah, so by this method you can calculate the value of total charge that is present inside the uh, uh, cube. Okay, so the total charge once you calculate will be equals to 8.854 pico coulomb. Okay, so let us move to the next question. So the question is current carrying component in a high voltage power equipment must be cooled to carry away the heat caused by the ohmic laws. A means of pumping is based on the force transmitted to the cooling fluid by charge in an electric field. The electrodynamic pumping is modeled in figure this which is given here. The region between the electrodes means these two electrode contains a uniform charge rho v, means here some charge will be present. Yeah, so here some charge will be present which is defined as rho naught, which is generated at the left electrode, means from here the charge is generated and collected to the right electrode. Okay, here charge is collected. So we have to calculate the pressure of the pump if rho naught is given as 25 millicoulomb per meter cube and V naught as 22 kV. So for finding such problem, we can use the Poisson's equation, which is given as del square V is equals to minus rho V by epsilon. Okay. So we will use the Poisson's equation and we will solve this question. So let us see here, as rho v is not 0 inside this uh, cylindrical volume, so that's why we will use the Poisson's equation. Okay, so one thing that we have to see here, that charge is moving only along the z, means variation of charge is present only with respect to z. So with respect to x and y, this will be equals to 0 variation of charge. Okay, so we can say that del square by del x square, del square by del y square, del square by del z square v is equals to minus rho v by epsilon. So there will be no variation along x and y, so that's why here we can directly write this equation as del square v by del z square is equals to minus rho v by epsilon. Okay, so we will first integrate this with respect to z. Okay, so first derivative of v is defined as minus rho naught z by epsilon naught plus a, where a is a constant. Okay, now we have to find out the value of v, so we will again take integration of this expression with respect to z. So the final expression of v is obtained as v is equals to minus rho naught z square by 2 epsilon plus az plus b, where a and b is a constant. So now for finding out the net expression of this potential, okay, we have to find out the value of a and b. So the question is how to find out the value of a and b. So for finding out the value of a and b, we will use the boundary condition. Okay, so here in the question it is given that the charge is generated from the left electrode, okay, and collected from the right electrode, means there at the left electrode the potential will be high, which is given in the question as well, that at the left electrode the potential will be plus v naught, whereas at the right electrode the potential will be 0. Okay, so we will use this boundary condition for finding out the value of a and b. So let us move ahead. So at z is equals to 0, will v will be equals to v naught. Okay, so we will put the value of z 0 here, so b becomes equals to v naught. Okay, from first boundary condition. Now the second boundary condition states that when z is equals to d, means when z is equals to d here, so the potential becomes 0. So we will use this and put the value of z in this expression as d and v as 0. So we can find out the value of a, which is given here. Okay, so you can put the value of a and b in the expression like here. So this will be equals to minus rho naught z square by 2 epsilon naught this will be epsilon naught plus rho naught d by 2 epsilon minus v naught over d times z plus v naught. So this is my potential field. Okay, so now for finding out the value of electric field, what I will do, I will just take the relationship between E and V as E is equals to minus del V, and we will take the differentiation with respect to Z only, because here in the expression of V it is dependent on the Z only, it is not dependent on X and Y. That's why in the here I am just taking the derivative of V with respect to Z only. So that's how you can calculate the value of electric field. Okay, so now once you find out the value of electric field, we know that the force uh, on a charge, let us say it's a q, which is moving inside a electric field, is defined as F is equals to QE. But here we are not solving for a single charge, we are considering for a volume charge. Okay, so here we will take a volume charge and define as rho v into E. Okay, and one thing that we have to note here, that E is also a space dependent quantity. See here that E is dependent on Z. Okay, so we have to take this E inside this uh, integration. Okay, so this can be represented as rho v, which is a constant here because it is given in the question, into ds, and this will be equals to E dot dz. So basically I am splitting this dv into ds dot dz because E is only dependent on z. So let us take this ds common here, and as it is given in the question that this area is equals to s, so we can replace this by into s, into we can integrate this function with respect to z. Okay, so that's how you can find out. So after finding out this just a second, yeah, so after finding out this integration, you will the find out the total force that is exerted on this becomes equals to rho naught s v naught into az. Okay, so this becomes equals to the total force. Now we have to find out the pressure. So pressure is basically defined as the force per unit area. Okay, so we have to just divide this expression by s. Okay, so this s will be cancelled out, and so that's how you can find out the pressure that we have to give uh, for cooling out this system. Okay, so that's how you can solve such type of problem. So now moving ahead, the last problem is a semi-infinite conducting planes, sorry, two semi-infinite conducting planes at phi is equals to 0 and phi is equals to pi by 6. So here is the first plate, here is the second plate. Okay, at phi is equals to pi by 6. Okay, this is phi and this equals to pi by 6, are separated by an infinitesimal insulating gap. So basically here a small gap is present, okay, which will separate these two plates. If v at phi is equals to 0, means at in this plane the voltage is defined as 0, and in this plane at phi is equals to pi by 6, the voltage is defined as 100 volt. So we have to calculate the value of V and E in the region between the plane. Okay, in this region we have to find out the value of V and E. Okay, so see here that here there is no charge is given between these two planes. So we will use Laplace equation instead of Poisson's equation. Okay, so Laplace equation is defined as del square V is equals to 0. So we will use this expression for finding out the value of V and E. Okay, so yeah, so del square V is equals to 0. So here we can see that the variation is present only in the phi domain. Okay, so that's why I am taking del square by del rho square and del square by del z square. So variation along these two will be 0. Okay, so this can be defined as 1 by rho square d square v by d phi square is equals to 0, and this can be further simplified as d square v by d phi square is equals to 0. Now we will take integration of this expression with respect to phi. So this the total voltage inside the within these two planes is defined as v is equals to a phi plus b, where a and b are the constant and which can be find out by using the boundary condition which is given in the problem here. Okay, so let us impose this boundary condition on this expression and find out the value of a and b. So at phi is equals to 0, v will be 0. Okay, so this states that b will be 0 here. Okay, so the next expression will be equals to v is equals to a phi only. Now when phi is equals to pi by 6, v is equals to 100. So you can put the value of v and phi here and find out the value of a. This will be equals to 600 by pi into phi. Yeah, sorry. Yeah, so this is my basically I'm sorry. Yeah, so anyway, uh, the total voltage is defined as v is equals to uh, v is equals to 600 by pi into phi. Okay, now you have find out the value of potential between the planes, between these two planes. Now for finding out the value of electric field, we will use this relationship between the electric field intensity and v. Okay, so we will use this expression relation for finding out the value of electric field intensity. Okay, so that's how you can find out the value of V and E by using the uh, Laplace equation. So basically, this problem states that uh, wherever, if suppose in a region no charge will be present, then you have to utilize the Laplace equation instead of Poisson's equation. Whereas, where in some region some charge will be present, so we have to utilize the uh, Poisson's equation instead of Laplace equation. So these all are the application of Laplace equation, Poisson's equation, boundary condition that we have covered in the week 7 of the course. Okay, so I hope this uh, content will be very informative to you. So with that, I thanks to all